Hello and welcome to lecture 68. We are discussing about CFD application to design and performance assessment. So, in last lecture we were discussing some of the important aspects for the CFD analysis application to axial flow compressors and fans. We were discussing about different boundary conditions. If we recall, we were discussing about inlet boundary condition, outlet boundary condition, wall condition, basically casing, hub, blade, that is what we are considering as a no slip condition. Then we were discussing about the periodic condition. We also started discussing about the domain interfaces, where we have discussed about mixing flow approach and we have discussed about the frozen rotor approach. And we realize in order to have what exactly we are looking for, say are we looking for detailed flow field study, that time some of the averaging, that is what we need to avoid. So, data that will be exchanged between rotary domain and stationary domain, that is what is being interfaced by using frozen rotor approach. We have seen how the data, that is what will be transferred from rotating domain to say stationary domain. And here in this case we have realized the clocking effect, that is what is coming into the picture, that is what is basically relative position between two domains. So, we need to be very careful when we are using one of the approach for say solving of stage, maybe say rotor stator or maybe rotor configuration for contra-rotating fan. Then we were discussing about the selection of turbulence model. We have discussed about BA model, we have discussed about SA model, and we realize for the initial stage of design where we will not be having flow separation, there we can go with those turbulence models. But we know when we are doing our initial design, we are not having clarity how exactly our flow will be behaving on the suction surface and on pressure surface, as well as what will be the flow behavior in the tip clearance region. And that's the reason why even at the design stage also people they realize we need to go with say KSST K omega model, which will take care of Coriolis component, and that is what is best model what people they are opting for say analysis purpose. Recently people they started talking about gamma theta model, that is what is giving idea about the transition of flow from laminar to turbulent, and we know that flow phenomena, that is what is very important. Some of the important flow feature we are missing when we are going with some other turbulence model. So, selection of this turbulence model is equally important when we are talking for say the accuracy of our analysis. We were discussing about the solver requirements, where we have discussed say compressible solver, incompressible solver. Those solvers also can be corrected as per the requirement, like we can go vice versa. Then we started discussing about the convergence criteria. So, exactly in sense of what parameters we are checking with or what analysis we are doing, that need to be observed. So, we will be putting some observed parameter with some RMS value or some average value, that is what will be continuously under observation, and that is what will give you the confidence in sense of the simulation, that is what we will be finishing or we already have finished with. So, that is what we need to realize here. Then we started discussing about different commercial packages for the CFD analysis. Now, the thing is, after having all this brief idea about the CFD and CFD tools and their processing, we must get some confidence in terms of using this say maybe understanding of CFD or say using our commercial packages. So, today we will be discussing about different case studies over the years what we have explored. So, let us take very first case study. This is what is a case study for contra-rotating fan. This is what I have explored when I was doing my PhD at IIT Bombay, And if you recall, when we were discussing the design of contra-rotating fan, similar kind of configuration we have discussed. Here we are having two rotors. If you look at carefully, say we are having rotor 1 and rotor 2. This rotor 1, that is rotating say in clockwise direction, and rotor 2, that is what will be rotating in anti-clockwise direction. So now in order to do design for this contra-rotating tool or say contra-rotating fan, we need to use the computational tool. So for that purpose we have used NCCFX for say solving this design or design problem. So before finalizing, we need to do or we need to go with number of iterations. So this is what will give you some confidence, some idea how exactly we need to use this tool after learning say mean line design or say preliminary design, what all we have discussed in last 11 weeks. So say very first step, that's what is coming as is a selection of parameters based on the restraints, which includes say speed of the rotors, annulus dimension, power requirement, mass flow rate and pressure rise. So actually we were available with say bell mount, that's what was having say inner diameter of 406 mm. We were having motors, they were having capacity of 15 kilowatt, and based on that we are having some constraints that need to be incorporated for the design. So maximum diameter, say rotational speed, power, they three were the initial restraints for our design. Then we have selected say geometrical parameters like aspect ratio, chord, number of blades, etc. So this thing what we are moving with say mean line design, the same way this is what is been done. Say vector diagram approach for determination of flow angles, different velocity components at the mean radius for both the rotors, calculation or say observed parameter what we learned say diffusion factor, degree of reaction, power based on what all number of blades we have selected with, distribution of aerodynamic loading as per the requirement throughout the span for both the rotors. And for current design or what design we are discussing, we have taken say highly loaded rotor 1. We were expecting our pressure rise to be 1100 Pascal for rotor 1, and for rotor 2 it was 900 Pascal. So total expected pressure rise from this contra-rotating stage, it was 2000 Pascal. Now after doing all this as a mean line calculation, we have calculated our camber angle, stagger angle, we have assumed our incidence angle, we have corrected our deviation angle, number of blades, solidity, chord, all those parameters, that's what is coming into the picture. Then next step, that's what is with the selection of aerofoil, that's what was stack about CG. We can understand both the rotors are rotating, and that's the reason why we need to stack both the blades or all aerofoils for both the rotor blades about CG. Then based on say available profile, say initially we have taken our C4 aerofoil for the design, and later on as per the requirement we have modified. So it says incorporation of modifications like number of blades, aerodynamic loading, flow angles, custom tailored blade profile, etc. in order to meet the design requirements. So this is what is a systematic way of doing the design. Now this design modification, that's what was done by using computational tool, and that's the reason why specifically I am putting this in a discussion. Now once we have finalized all our dimensions, later on we made our experimental setup for both the rotors. Here in this case, initially we have started doing design with say expected pressure rise of 950 Pascal and 800 Pascal, and we have understood like how exactly my aerodynamic loading, that's what is happening on say pressure surface and the suction surface for say both the rotors. So this is what is representing at different span location for rotor 1, and this is what is representing say aerodynamic loading at different span for rotor 2. Then slowly we have increased our aerodynamic loading as per our expectation to 1100 Pascal and 900 Pascal. So when we have done this part, for that we have initially fixed our number of blades based on number of iterations. Then we need to go with, say, for this particular aerodynamic loading, whether this number of blades will be coming to be as per requirement or not. Let me tell you, here in this case our blades are high aspect ratio blade. So we can understand the height of the blade is large and chord is smaller. So we can say 135 mm, that's what was the height of the blade, and 45 mm was the chord of both the rotors. We can understand this 45 mm, and within this blade passage to do diffusion, that's what is very challenging. But that's what is a challenge for the design, and that's what we have opted for. So with this we have done number of iterations in sense of modifying the deviation angle. With modification of deviation angle, we can see the aerodynamic loading for both rotor 1 and rotor 2 at different span, that's what was getting changed. Still we were unable to achieve what pressurized we were expecting. Later on those aerofoils, they were being modified. So you can see this blue color one, that's what was original C4 aerofoil. Later on we have modified by shifting, say, maximum thickness point as well as reducing the thickness of this aerofoil, and by doing so we were able to achieve the pressure rise as per our expectation. So by having this kind of initial study, by having, say, initial analysis, we will get the confidence about the design. Again, let me put you point here, this CFD is not a design tool. This is what is for design verification. Okay. Now once this is what is been done, we have developed our experimental setup, and here if you look at, we have discussed earlier what all are the benefits of contra-rotating fan, where we have discussed about the partial stall and full stall configuration. I will not be repeating here. And here if we look at, say, these fill points, they are representing, say, experimental results for different spacing between both the rotors. Now in design, at the design stage, when we are doing preliminary design stage, that time this spacing will not come into the picture. But when we are doing our analysis or when we are making our both the rotors, then what need to be the distance or axial spacing between these two rotors, that's what is very important. Okay. Basically that's what will be deciding your aerodynamic performance, that's what will be deciding in terms of, say, your expected noise as well as the length of your stage. Suppose, say, we are designing, say, multi-stage configuration for contra-rotating application, that time the spacing between these two rotors, that's what is very important. So this is what is representing, say, 0.5 chord axial spacing, 0.9 chord axial spacing and 1.2 chord axial spacing. Initially when we started doing design, that time we have assumed our axial spacing to be 50% of rotor chord 1. Later on by experimentation we realize 0.9 chord or 90% chord of rotor 1, that's what is a spacing, it is giving improvement in terms of performance, and that's what was later on been used for all analysis purpose. This is what is representing the validation. So if you look at this unfilled points, they are representing, say, CFD analysis. If you observe carefully, for the high mass flow rate configuration, it is not matching well, it's having certain amount of discrepancy. But when we are moving towards, say, peak pressure point, that time it is matching well for all different speed combinations. Later on, after having experimental result, say, as we have discussed your inlet condition, you can take, say, variation of total pressure. So having, say, experimental results, we have considered that profile as input, say, total pressure input. Same way we have used 7-hole probe for the measurement of velocity. With that boundary condition also we have done our simulation, and that's what was being used in order to validate our say CFD and experimental results. So here this black color one, that's what is representing our experimental results, and that's what is representing our CFD results. So if you observe carefully, like for rotor 1, when we are having say design mass flow configuration, that time it is not giving much comparatively good agreement between experiments and computational work. But when we are talking about say for rotor 2, it is matching well. At the same time, as we have discussed here, say during peak pressure configuration or say peak pressure mass flow rate, it is giving very good agreement between experimental and computational results. Now this is what is a question what we say in terms of limitations of your computational fluid dynamics, or still it required a lot of digging inside in order to achieve the validation of experimental as well as computational results. Now based on the confidence what we built for say contra-rotating fans, this is what is a second work, that's what is going on at IIT Kharagpur. It is project Airavat. We are developing our flying car, say prototype model of 10 kg, that's what is in progress. In order to have that, this is what is our proposed model, in which we will be having say ducted fans on the front side, we will be having ducted fans on the rear side. Now in order to have say lightweight, we have discussed these aspects when we were discussing the industrial fans. Rather having big size single fan, it's preferred to go with number of fans, or say maybe going with say number of motors. So that's what will be giving benefit in terms of say weight as well as what we are talking about the endurance and motor capability, and that's the reason why we have gone with this multi-fan configurations. Now here when we are flying at the cruise condition, say this is what is say vertical takeoff kind of configuration, where we are having say telescopic wing, that's what will be giving the benefit in terms when we are going for say cruise. When it is on road, it will not be having say extension. So during cruise condition, rear fans, that's what will be getting tilted, and that's what will be giving the forward movement. Now the question, there are many questions for such kind of proposals when we are doing say development activities. The very first question that has come, what need to be the spacing between these two fans? Now let me put one point here, say we have realized the advantage of contra-rotating fan, and that's the reason rather going with the single fan or say maybe stage, we have gone with the contra-rotating configuration. So these are the two contra-rotating fans, they are being ducted. Okay. Now what need to be the spacing between these two, because that's what will be deciding. Suppose say it is a roadable vehicle, then we are having constraints with say sizing, and that's the reason why we have explored the possibility for say what need to be the spacing between these two rotors, and we found that need to be say 2 times the diameter of the casing. The benefit of contra-rotating we have explored with say different requirements, say higher rotational speed of rotor 1, higher rotational speed of rotor 2, both the rotors are rotating at design configuration. Basically that's what will be helping us in order to manage the thrust. So that's what we have done here. So this is what is representing the total pressure contour at the exit plane, and this is what is giving you new horizon for the thought process for future development of flying taxis. So like what all we are learning, that's what is having say straightway application for the future development. Okay. So you can see here earlier design, that's what was high aspect ratio blade. Here these blades are low aspect ratio blades, and that too, that's what is handling different kind of flow configuration, and their purpose, that's what is totally different. This is what is the case study what we have discussed in our week 11 for the design of say wind tunnel fan. So this is what we already have discussed say at IIT Kharagpur Center for Reliability Research. We are having say development of this closed loop wind tunnel. This project, it has been sponsored by RDSO, Indian Railways, and these are the requirements for the fans. That's what we have discussed, already discussed with say mass flow rate of 420 kg per second, the expected pressure rise in order to get rid of frictional losses, that's what is 1400 Pascal, diameter is 4 meter, and if you look at this is how we have done our initial design for the fan, where we are having rotor and stator configuration. If you recall, we have discussed design in a different aspect. We have discussed with say design in terms of say having number of blades. We have discussed about say chord selection. We have discussed in sense of diffusion factor. Then we have discussed about what all are the requirements of stator and rotor. So if we go ahead, this is what is representing. So if you recall, this is what will give us idea with less number of blade and more number of blade for the rotor. We must realize the passage between two blades, that's what is the diffusing passage, and that's what is following what all rules we have discussed in terms of length of the diffusing passage, say diffusion angle, inlet area, outlet area. So based on number of iteration, we have come up with say combination of 16 and 17 blade. This is what is a design what we have discussed in week 11, and we have explored our computational study, and that's what is giving say best performance in terms of what we are expecting. So here if you look at say initial original blades were like this, and later on we have done our modification in terms of number of blades. We have done our modification in sense of shape of the leading edge. We have done our modification in sense of chord length, and if you look at this is what is representing the final results or say finally selected geometry. Here in this case, this is what is representing say overall pressure rise or say pressure rise from the stage at the exit. So when we were having our initial design, that time it was giving the pressure rise here. This is what is representing the modified design, and here if you look at this is what is representing how my stream wise pressure rise, that's what is happening. So here in this case we can say this is what is representing our stator and rotor combination, okay, and this is what is our total pressure, that's what will be developed by this particular fan. So as per our requirement, we need to do certain modifications. So as we have discussed, we have done our initial design based on what understanding we are having. Later on, by using computational tools, modifications they are being done to meet the requirement, okay. Now let's move to our next case study. So we have discussed the present trend, it is looking for say compact and lightweight compressors. Compact in the sense the length and diameter need to be smaller, lightweight in the sense number of components need to be lower, and in order to achieve those requirements, per stage pressure rise requirement will be very high. And we have discussed in order to improve per stage pressure rise, we need to go with say larger diameter, or maybe we need to go with say larger rotational speed, or maybe we need to go with say higher axial velocity. We have discussed what all are the challenges when we are talking about all these aspects. Now the situation is when we are having one more possibility is to increase the deflection angle. So here if you look at in order to achieve high pressure rise, my delta beta need to be larger. So if we are increasing our delta beta because of adverse pressure gradient, there are more chances for flow to get separated from the suction surface. Now when it is getting separated from the suction surface, we can say that particular aerofoil or that blade, it is tall, and very soon whole stage will be going in surge, and later on whole or all compressor stages will go in surge. That's what is very challenging aspect. So in order to address this issue, people they have explored the possibility of tandem configuration, where we are having two blades, they are being placed and considered as a single blade. So in place of having one blade, we will be having two blades. That's what is been arranged on single rotor. I will show what exactly is the meaning of that. If you recall, in week 3 we were discussing about what all are the possibilities for the design. Let me discuss here what we learn for say tandem configuration. We want to take the benefit of flow. So here this is what is the region. Basically the trailing edge of my blade 1 and leading edge of my blade 2, that's what is acting like a nozzle, and that is helping us in order to accelerate the flow on the suction surface of say next coming blade or blade 2. Now when we are doing this, this is what is giving the benefit. This work, it has been explored initially for the wings, and later on people they tried to explore for say rotor as well as for stator also. So there are two main configuration we need to realize. One, that's what is say my axial overlap. So we can say this is what is representing the axial overlap, and this is what is representing the percentage pitch. Limited work it is been reported in order to do the design for tandem bladed rotor, because that's what is very challenging. Now number of data and results are available for cascades, but we can understand at particular station all my configuration may be working fine, but after having background of all 11 weeks, you must realize my blade, when we are talking, it is say for rotor, it is not at particular station. This is what is a three-dimensional entity. So we need to think design in three-dimensional way. So this is what is represented: 0 axial overlap, minus 5% axial overlap, 5% axial overlap, and 3% axial overlap. So you can configure near the hub axial overlap is 0, and at this location near the tip region my axial overlap, that's what is varying in terms of percentage of say my chord. Now these are some of the important observation. As we have discussed, the use of computational tool, that is very important. So here if we look at, this is what is representing say the case for say 0% axial overlap. So this is what is representing my axial velocity. If we look at carefully for the 4 blade, we are having this as a tip leakage flow. So we need to provide certain amount of clearance between casing and the rotor blade. For our case, we kept our tip clearance as 3 mm, and that's the reason you can see this is what is a tip leakage flow. That's what is coming out from the 4 blade. Now this particular region, because of this nozzle effect, we are having the acceleration of flow that is happening between these 2 blades, but at the same time the flow, that's what is coming out in terms of tip leakage flow, that's what is say exiting here. At the same time, if you observe carefully, because of this turning of the blade, we are having the separation that is happening near the trailing edge for our aft blade. Later on, this is what is being modified in terms of point say 5% or minus 5% axial overlap. Here in this case, not much benefit in sense of nozzle effect it is been found, and that's the reason why my trailing edge, say upper portion, say maybe 70% of the span, if we look at, there is a flow separation that is happening for aft blade. So this is what is not the promising configuration. Later on it has been moved with the 5%, and if we configure here, my acceleration of flow between this blade passage is such it is giving benefit in sense of removing the trailing edge separation. That's what was happening on half blade. Later on we have optimized with the 3% axial overlap, and if we look at my extent of this flow, what we say rollout or the secondary flow, what we can say the extent it is reduced. Okay. Now if we look at, we have understood, suppose if we consider, say this is what is my rotor and stator combination, because of my growth of boundary layer along the casing and deep leakage flow, particular region, that's where I will be having low momentum fluid or say low mass flow rate, and that's what will be acting like a pocket or say zero velocity kind of region. When that's what will be striking on the stator, the challenge for the design of the stator will be increasing. So here if you look at, this is what is a flow or the blockage, that's what is coming out from say our tandem bladed rotor. Now this is what will be striking on the stator. So that's what will be making the design for the stator to be very challenging. And if you look at, this is what is say the exit total pressure loss coefficient. If we observe my exit total pressure loss coefficient, that's what is coming to be higher. We can say we are having the separation of the flow, that's what is happening on the suction surface of the stator. Let me put one important point here, say conventional stator and rotor combination, only one wake, that's what will be coming out from my rotor blade, and that's what will be striking on the stator. Now for this tandem bladed configuration, there are two wakes, one from foreblade, one from aft blade, they both are striking on the stator. So that's what is making design of the stator to be very challenging. Now these are the modifications, this what we have done in order to achieve what we are looking for in terms of total pressure rise. So this is what was initially been designed or conventional stator, where we are having say losses, that's what is happening. Now later on it has been modified with end wall dihedral. So you can understand this is what is a three-dimensional stator, and our computational tool, that's what is helping us in order to modify the design. For our quick solution, you can understand, like if I will be making number of iterations, for all iteration if I will be making blade and then after I will be doing my experimentation, that's what is required a lot of time. So we are able to reduce number of iterations required for the experimental study, and that's what where the cost is coming into the picture. Now this is what has been final design with say re-staggering of the stator blade. So here we are able to manage our flow at the exit of the stage. Now this is what is representing how my total loss coefficient, that's what is getting modified for both the stator configurations. So this is what is a final state or final design of the stator for tandem bladed rotor. So must realize it is easy to say, like using tandem bladed rotor we can get high total pressure rise, but at the same time the design for downcoming stator will be very challenging. Design of rotor itself is challenging, at the same time design of stator also is equally challenging. Now this is what is experimental facility which has been developed at IIT Kharagpur. If you look at, these are our rotor blades and stator, and very soon we will be having say outcome from the experimental results, which will be the helping hand for the future researchers as well as for the future development and help to the society. There are some more configuration what people they are exploring, that's what is based on bio inspired say compressor and fan blade. So here if you look at for this eagle, the end, say we are having tip region where these feathers are arranged. That's what is helping them in order to minimize the drag. The same logic, that's what has been applied at University of Cincinnati for the development of say compressor rotor blade. So they have splitted this blade in two halves, and by doing so they are able to improve the performance in terms of operating range. Basically how we are managing our flow in the tip region, that's what is very important. Similarly, this is what is a concept called tubercle effect based on say humpback whales. So here if we look at, that's what is having some surrogated surface, or that's what is in technical language people used to say tubercles. This is what is helping whales in order to say minimize the drag and to propel. So same logic, that's what is being used for development of say open fan configuration, even these days for say cooling of say computers, servers, high speed computers. We are looking for cooling fans. They are making a lot of noise, and in order to address this issue, that surrogation people they have adopted near the trailing edge. Even people they are exploring surrogation at the leading edge. So this is what is one of the bio-inspired kind of configuration. Now people they are talking about say casing treatment. That's what is to enhance the operating range and with having say certain compromise in the efficiency. So there are different configuration people they have explored. It's called say blade angle slot. So here you can look at, this is what is a blade angle or blade aerofoil at the tip region, some honeycomb section, perforated kind of configuration, circumferential groove, screw slotted on axis say slaughter or say axial slots people they have explored. Now in order to decide this kind of configuration, the computational tool, that's what will be helping a lot. There are many open literatures available where people they have explored their computational tool to finalize the geometry for the casing treatment. Now there are different configurations, say stagger angle, skew angle, axial position. That's what is very important. Maybe we need to go with say recirculation, maybe blowing, sucking, all those terms, that's what will be coming into the picture. And computational tool, that's what will be helping hand for this kind of simulations. So in overall, if you look at, CFD is now helping hand for the design and analysis for different turbo machinery. Now the use, that's what is been increasing day by day, because we are able to simulate high speed flow with high fidelity methodologies. Now we are able to control say secondary flow phenomena, even say the corner separation for the compressor and turbine blade, and that's what is helping us for analyzing the three-dimensional flow that is happening between the blade passages. Say modern turbo machinery design, that's what is rely completely on CFD, but still I'm putting point here like CFD is analysis tool, it is not a design tool. So initially you need to do your preliminary design using your Excel sheet, what all we have discussed. Later on you can use this as a tool for the simulation and finalize your geometry. Now CFD, that's what is giving very good prediction in sense of change of direction and reliability of the results. This is also helping in terms of say three-dimensionality, what we have discussed, secondary flow, say tip leakage flow, say corner separations, those all terms, that's what is now we are able to achieve. There is a recent trend, it says this CFD, it is been used to solve the problem of distortion. So for future engines, we are looking for say distortion tolerant fan that need to be used, and at the design stage only if we are taking care of, This is what will be helping us for the development activities. So here we are stopping with, we have discussed about different case studies, what all we have explored over the year for the design and development activities. Even at the same time, in order to do number of iterations in design, we have discussed some of the bio-inspired configuration, we have discussed about the casing treatment, and we realize we are having the advantages of using this CFD analysis for axial flow compressors and fans. So here we stop with. Now in next lecture we will be discussing about very important aspects. We say what all are the challenges of CFD application to axial flow fans and compressor. Thank you very much.